Hi and welcome to this section where I would like to look at the powers of a complex number. Okay, so we start this by looking at what we call the Morpheus Theorem by first expressing our complex number z in terms of exponential form. Its modulus r, e, j, and its argument theta. Okay, so if we say if we want z raised to the nth power, definitely it is going to be also the right hand side. We are going to raise it to the nth power, and then this is what we come up with. Okay, and then we can write this again in polar form. Okay, and this is going to be the r to the n, and then this is going to be cos, and now its argument is going to be n theta, then plus j sine n theta, and this result is our well-known Demovires theorem. So Demovires theorem, we can make use of it here in maybe trying to evaluate the nth power of a complex number. For instance, we have our complex number z, which is equals to 1 minus j. Now we want to find z raised to the 12th power. Okay, however, we have already seen from the Demovires theorem that z raised to that is going to be that cos n theta plus j sine n theta. Okay, so all we need to do is to find r, okay, the modulus, which is found here, and then we also need to find theta, the argument, which is found here, 1/4 pi, and then the rest is just to substitute. Okay, before we substitute, perhaps we write it back in polar form by saying 1 minus j can be written as r cos theta minus j sine theta. Okay, its modulus and its argument here. So now we can say that now 1 minus j raised to the 12th power is simply going to be r to the 12th power, which is root 2 raised to the 12th power, then cos n theta. Okay, this is the next step here. N times the theta, and also here n is the 12, then times the theta, which was 1/4 pi, and this is 1/4 pi. Okay, so the rest is just substitution. Then this becomes cos 3 pi, and then this becomes sine 3 pi. We know that sine 3 pi is 0. Okay, and then we know that cos 3 pi is -1, and then 2 to the 6 is 64 times the -1, which becomes -64. Okay, so we can as well use this Demovires to find the nth root of complex numbers. Okay, for example, what if we want to find the nth root of z? So we have our z, and then we want to find our nth root. We can start by saying that maybe we can set our w to be equals to z to the nth power, and then we will have, of course, that w to the n equal to z. So we can say that maybe w is our complex number with a modulus capital R, and then maybe we have cos phi, okay, plus j sine phi, and then z maybe with just the modulus lowercase r cos theta plus j sine theta. Okay, so we can see we have an expression for w to the n. That means that w to the n, okay, we know it is going to be r to the n, then cos n phi plus j sine n phi. Okay, do we have an expression for z to no? Okay, we can as well now just move on. So here we can just now wait a minute. So what next do we have? Okay, so we have w to the n. Okay, so now we are on this step here. w to the n is equals to z. So we have our w to the n, which is this, and then we have our z, which we said is just that. So if w to the n is equals to z, we know that if two complex numbers are equal, then we equate real part to real part, imaginary part to imaginary part. So here we equate the two real parts. This is r for z, the real part, and then this is the real part for w to the nth power. And then next, this is the imaginary part for wn, and then this is the real part for z, sorry, the imaginary part of z. This is the imaginary part, this is the real part of w to the n, and then this is the real part of z, and this is the imaginary part of w to the n. So a series of algebraic, first you can square both sides, both equations. So if you square both and add, so what you have r squared or squared theta. We can pull out r because it is common here, plus sine squared theta, then equals to r 2 to the n. Okay, we are squaring also the right hand side, and then what do we have? We have cos squared, you have cos squared n theta plus sine squared n theta. Okay, and so we know that this is 1, and we also know that this is 1. Therefore we have that r squared is equals to r to the n, and therefore if we take square roots and square roots on both sides, we see that r is going to be equal to okay, what expression do we want? We want for r or capital R. Anyway, let's see. Okay, we can take that the half, I don't know how to, it's not okay, we can take that root 1 over 2n, that 1 over 2nth root, and then we shall come up with now r being equal to r to the nth root. Okay, the expression we have here. Now again we can substitute this value back into the equations, any equation here. Maybe we can substitute it back here first, then you find that you substitute for r is equals to 1 over n, whichever, whether we had found r in terms of r as a function of r, or we had found r in terms of function of r. Either way, it doesn't matter. You still come back and substitute for r here, okay, or for r here, and then you come up with this equation that cos theta is equals to cos n phi, and then also sine theta is equals to sine n phi, when we also do the other substitution in this equation here as well. So from there, okay, from that, then we can as well now say that this pair here of simultaneous equations, if we solve it, okay, if we solve this for n phi, we shall find that it has infinitely many solutions, okay, and the solution is given by n phi is equals to theta plus 2 pi k, okay, where k is an integer. Okay, so when we divide both sides by n, we shall see that our phi, okay, is just theta over n plus 2 pi k over n, where k, okay, is the integer. Of course, the integers are positive or negative whole numbers, so that's why you have 0, 1, negative 1, 2, negative 2, and so on and so on. So now that we have everything, we are going to substitute these values for r and phi into the formula for w, because remember we started by saying that let w here, we started by saying that let w be equals to z to the nth power. So we see w equals to z to the nth power, but we know that w, we said, was r, okay, cos phi plus j sine phi. Okay, now we have r, which we found in terms of what we already know, which is that, and then we have cos, and then we have found out our phi from solving these two simultaneous equation, this simultaneous equation, okay, given by equation 1 and equation 2, solving that simultaneously. And now we have found out that that is theta over n plus 2 pi k over n. Then we have plus j sine phi, which is the same theta over n plus 2 pi k over n. Okay, and that is it. So that is our and if we have to find the nth root of our z. Maybe one important thing to note is that k is an integer. We have already mentioned that, but then that this expression, since we are finding the nth root, it yields exactly n different roots corresponding to k ranging from 0, 1, 2 up to n minus 1. Okay, up to n minus 1. That is important to note. For example, let us see. Okay, you can okay, you see this is just the same as whatever we have here, but we are just writing it in exponential form. This is r, its modulus r, the power 1 over n, then e, j, then the argument which we have here, which is theta plus n, this one here, okay, theta over n, not theta plus n, sorry, theta over n plus 2 pi k over n. Okay, so what next? Okay, so we look at an example here. So the example, we are given z as we have, this is our z, and then we want to find z to the power half. So we are going to say that let w be equal to r. Do we go through all this, or we can put straight in the formula? Anyway, we don't have to go through all this. Maybe we can just write down the formula and then say that we know that z to the power 1 over n is going to be equal to r 1 over n. Okay, then we have cos n, and what do we have here? Theta over n plus 2 pi k over n plus j sine theta over n plus 2 pi k over n. Then the rest is just for us to substitute. R, we can find r. How do we find r? R is simply the modulus, which is the square root of x squared plus y squared. Okay, and then we have 2 to the power negative 1/2, and then we find the modulus here, theta, which is the argument of z, and then okay, I'm sure by now, if you've seen the previous explanation, perhaps you know why we have theta minus tan inverse of 1. It's because of the where the angle is located, okay, and how it is being computed. So, and then we end up with 3/4 pi. Okay, so the rest we just substitute. So we have z is equals to r, okay, r to the power r, oh, what did we first find for r? R is this, okay. So in here, oh yeah, sorry, we just z, not z to the power 1 over n. Okay, this is just z. So this is r, then cos the theta plus j sine theta. Okay, And then we can now say that z to the power 1/2 is going to be r to the power 1/2. Okay, we have already written this down. Okay, and now you realize, because they say that the integer is going to run 1 up to n minus 1. In this case, our n is 2 because we are finding the nth root, the second root. So we just have k is running from 0 up to n minus 1, which is 2 minus 1. That is why you have k is just 0 and 1. Okay, so we are going to compute this expression here for only k is equals to 0 and 1. So the rest is to substitute. Okay, so remember that r was 2 to the power negative 1/2, but then the formula here says we have to have r to the power 1 over n. Okay, so that is why we have r to the power 1 over n is, okay, to be precise, r to the power 1/2 is going to be that negative 2 to the power 1/2, and that is why you have 2 to the power negative 1/4, what appears here. So please be careful. Okay, so as you know, because that is what was going to confuse me slightly here, this is just z. Okay, then again you have z to the power 1/2. Okay, and then okay, the rest is again substitution. So we have in the formula here we had theta over n. So what did we get for our theta? Was it up here? Yes, our theta was 3/4 pi. So 3/4 pi you divide by 2. Okay, this is 3/4 pi divided by 2, you get 3/8 pi. Okay, then plus 2 pi k over 2, okay, over n. So 2 pi k over n, which reduces to that, and then the rest, this is the same. So the first root we consider k is 0, so you just substitute k is 0, that is 0, that goes out, and then that goes out, so you have this. And then the second root, k is 1, then you substitute for k is 1, and then you can, you know, add this to that. So when k is 1 we have pi, and then when k is 1 we have pi. So 3/8 pi plus pi, that is 11/8 pi, and then yes, for k is equals to 1. And then the rest is just for you to evaluate them. Okay, and see and verify that cos 3/8 pi is what is given here, and then sine 3/8 pi is what is given here. And for the second root, you verify that sine 11/pi is what we have here, negative 0.7769, and that's the cosine of that. Oh, actually it's not just that, but the, you know, the values here multiplied by what we have here, because this is the final answer. So just compute the final answer and make sure that even after you've multiplied by this times the value here, you have these correct answers here. Okay, so the rest is the same, by the way, even if it is now we want to find the cube root. Is whatever changes, we do exactly the same thing, only that instead of now 2 we have 3, but it follows the exact procedure. Okay, all right. So even when we want to, you know, find to the rational powers of z, you know, if we want to find the rational power, maybe zp, where p is m/n, it is just the same. So let's see how it comes about. So we can say that z to the p, since p is n/m, okay, then z to the p can be written as z, no, this is m/n, sorry, not m/n. So we can first find the nth root, and then we can first find the nth root, okay, and then we power it, power m. So what we have here in the brackets is what we have already seen. If we want to find z to the power 1/n, the nth root of z, it is this r, and then we have this, okay, n theta over n plus 2 pi k over n, then plus j, you know, theta over n plus 2 pi k over n. That one we have already seen. Now after doing that, now again we have to raise it to the power m, and that is what we have here. Remember, this is valid for k is equals to 0, 1, 2 up to n minus 1. So if we raise it again to the mth power, now we are going to make use of what we have already seen from our Demovires, okay? So we are going to have now the power multiplying by here, okay? And then also now it will multiply by whatever we have inside here from Demovires, the first thing we did. So that is why we have r to the power m over n, then cos, then this becomes m theta over n plus 2 pi k m over n plus, you know, that. And yeah, we can write it because we know m over n is p, so we can remove this and put p theta, and then the rest is just the same, okay? So it just follows that even if p, I mean, we have a rational power p, which is m over n, is just exactly the same thing here we just have here. For instance, if we want to compute this raised to the power negative 2 over 3, we are going to do exactly the same thing. We are going to say that our z is negative a half plus j 1/2. Then we find the modulus, okay? It's not found here, maybe it was computed already. Have we computed the modulus before? Okay. I want to finish this quickly. I think, what was the previous one we have done? Let's see, was it the same? If it is the same, then perhaps we're just carrying over. Yes, it is the same. Negative 1/2 plus j 1/2. So we just carry over. So this is negative 1/2 plus j 1/2. So we just carry over. So we have r. So we have r, I think, which was 2 to the power negative 1/2. That was r. And then I have, I think, that was our theta, our principal argument. So what do we have here? So if we have z to the power negative 2 over 3, so it is going to be equals to r to the power negative 2 over 3, but r was that. Then if we want r to the power what is it, negative 2 over 3, then it's going to be negative 2 over 3, and I suppose, yes, times that. So I suppose this one here turns out to be 2, then this and that go negative and a negative, so you have 2 to the 1/3. So we have 2 to the 1/3, then cos, okay, of whatever we had. Then we have multiplied everything by negative 2 over 3, okay? So whatever was in there, first we had n over theta, okay? Why are we suffering with this? It is just p theta, where p is negative 2 out of 3, and then our theta, we had it as 3/4 pi, okay? So this and that, and then this is 1/2, okay? Yes, 1/2, negative 1/2 pi, which is that. Verify the rest here. This is okay, and then you can verify that, okay? Remember, we have m over n, okay? Our n is 3, okay? Our n is 3. Please remember, our n is 3, because yes, our n is 3. It's like we are raising this first to power negative 2, and then we take the cube root. So our n is 3, and that is why our k is ranging from 0, 1, and 2. So we are going to get 3 different roots. We'll substitute in first for k is 0, and then we get the expression and compute, and then for k is equals to 1, expression and compute, and then for k is equals to 2, expression, compute it, and simplify it, okay? So I hope that is clear. You can take your time, you get your pen and paper, and also go through the examples. They are really well explained here. So we'd like to look at this example as well. They say solve the quadratic equation here. So the quadratic equation, you can see is in terms of z. This is z squared, then this is the coefficient of z, and then this is the constant. So one can use the quadratic formula method, which is used here, suppose. Okay, the quadratic formula method, you use it here. And then in that expression, we'll come up with this negative 2j minus 3 plus or minus square root of negative 15 minus 8j. So you realize that now you have to compute, that complex number z, which is negative 15 minus j8, but then we want to raise it to take the square root of that. So again, we just compute it like we have already done. So this is our j. We are writing it in polar form, and then now z. Sorry, this is z written in polar form. Then z to the power 1/2 is simply going to be r to the power 1/2. Then cos, n over theta plus 2 pi k over n, which is 2. Okay. This is theta over n. So theta is this one here, and then we divide it by our n. Okay, and what else here? Yes, this also divide by n. This is 2 pi k divided by n, which is 2. Then minus this, and so on. Okay. So yeah, what next? Okay, please remember here that our theta is a negative, and yet when we are writing cos, we just put it as a positive here, because we know that cos of negative theta is the same as cos theta. Okay, and please remember we say that sine of negative theta is the same as negative sine theta. So just for convenience, rather than carrying cos negative theta and so on, it's just convenient that you just write cos of theta, although the theta here is a negative. And then here where it was negative, we have the negative j sine, the theta. So that's how it moves. So here we have computed that, and then two roots, of course, for k is equals to 0 and k is equals to 1. So we substitute for k is equals to 0, k is equals to 1, find the 2, and then substitute them back in here, because remember, we are trying to compute this one here. Okay, we are trying to compute this quantity here. Alright, seems pretty long, and I suppose you have quite a lot of work to do. You can get your hands dirty by getting pen and paper and then working this out step by step. If there's any question, you can put it in the comment section. So thank you for listening and or watching, and see you in the next session. Bye bye.